Good morning, sir.
Is the screen and voice clear?
Yes, sir.
CS, is the 10 to 11 session completed?
We're not having 10 to 11 sessions today.
There's no 10 to 11 session. Okay. What is our class strength?
60.
60. Okay. Why still there is 46? I hope that still the 10 to 11 session is going on. That's why the delay in joining to this session. CS, kindly post a group in your message in your class group to join the session soon.
Yes.
Yeah. So good morning, everyone. In the previous session, we have been discussing about the basics of the formal languages, right? I have touched upon all the basic stuff. We had a class yesterday, right?
Yes.
Sorry guys, my schedule is a bit hectic. I'm taking two flat for you, B1 and B13, and also I'm taking compiler design for the CSBS third years as well. So there's a lot of content for my classes schedule. Yeah, okay. Yeah, so in the previous class, we have discussed about the formal languages basics. I'll just touch upon very briefly, just to have a recap of what we have discussed in the previous session. We have discussed about symbol, right? The basic characters in formal languages are symbols, not alphabets. So 0, 1, A, B, all the symbols, so on. So each and every individual character, we call it as a symbol in formal language. Next, we have alphabet. Yesterday I have forgot to explain about the notion. Alphabet is denoted by the symbol sigma. So in the course of our semester in formal language, whenever you find sigma, treat it as alphabet. So alphabet, I have explained in the yesterday class, it specifies mostly the range. So sigma 0, 1, this is the writing notation of the alphabet. So this specifies that all the strings over the alphabet 0 and 1. So if I take length of 2, it will be 0, 0, 0, 1, 1, 0, 1, 1. So we call it, these are the strings over the alphabet 0 and 1, over the sigma or over the alphabet 0 and 1. So 0 and 1 essentially specifies the range of the characters. So this is 2 length. If I take the 3 length, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, all such possible combinations. Okay. So we call alphabet as a range, not a character. Character is a symbol. Each and every individual character is a symbol in formal language, and alphabet is range. What are the symbols that we are dealing with? So that's we call it as alphabets. These we call it as strings. So any possible combination of the
Excuse me,
yeah.
sir. Actually, you didn't teach. Last class, you just said history about flat, and you said you'll start actual class from today.
Okay, we haven't discussed all these basics, ma.
No, sir, we didn't.
Sir.
Okay. Thank you for bringing it to my notice, ma. See, this is the problem. I have discussed it in the other section, and I thought it has been covered for you as well. Yeah, sorry. So now we'll start about some basics of the formal languages. So the difference between formal language and the normal language, for example, English. English is a normal language, not a formal language. Okay. So in English, the basic is alphabet. From alphabets like A, B, C. From alphabet, you have words. Words make sentences, and all the sentences plus grammar, that makes me language. Right? So coming to the case of formal language, there is a difference. So here the least possible entity is alphabet. Here the least possible is symbol. Okay. Any individual unique character is a symbol in formal language. Be it a digit, a special symbol, or the general alphabets in any case. So one individual character is a symbol. Okay. Next, alphabet. So in formal language, alphabet is depicted by the symbol sigma, and we call it generally in the, like we talk alphabet in the case of range, like this. So 0, 1 is the alphabet. So just now I have discussed all the strings, right? So these are the strings over the alphabet 0 and 1. We use the phrase over. Okay. So strings are any possible combination of the symbols over alphabet, range 0 and 1. So for example, 0, 0, 0, 1, 1, 0, 1, 1. So these are the strings of length 2 over the alphabet 0, 1. 0, 0, 0, 1, 1, 1, or 1, 1, 1. These are the strings of length 3 over the alphabet 0 and 1. So this is how you need to address the notation. Okay. So we haven't discussed about the clean closure, positive closure, all these things, right?
That's it, but some basic points, is it? 2 or 3
We
points.
have discussed prefix and suffix, right?
Yes, sir, we discussed.
Yeah, that's it. That's it. Very much the basics. Nothing much to explore. Yeah. Okay. No problem. So we have clean closure. So in clean closure, there is empty string. Apart from all the collection. So for the same example, over the alphabet 0, 1, if I want the clean closure of length 2, there will be epsilon, the null string, as well as all the 2 length strings. So from the same clean closure, if I subtract epsilon, I will get all the other strings, right? This is called as positive closure. Okay. So we discussed about the empty string. Mod of E is 0. Okay, so modulus, the length is 0. That's why it is called as empty string. We discussed about prefix, suffix, and all these things. So basically, all the basics of the set theory that you might have studied in your mathematics in schooling or +2 level, the same stands for formal language also. The same property of union, concatenation, the associativity, all the same things that will be applicable to formal language also. For example, string 1 is AB, string 2 is CD. If I take concatenation S1, S2, the result will be ABCD. That is the concatenation. So if I have set AB, set CD. If I want union S1 to S2, it has all the things, right? A, B, C, D. The same properties, the intersection, everything is same. I don't want to touch upon those boring topics again. Okay, so this is pretty much the basics now. This is all what you require from the formal language, but nothing much. Okay, just know the symbol, alphabet as you specify as the range, strings, clean a closure that contains epsilon, positive closure doesn't contain epsilon. So generally clean a closure is represented as sigma star. So for an alphabet star means clean a closure, you should be having null string. So for the same epsilon plus is positive closure. There's no null string in it. That's it. Okay. So these are the basics of the formal languages. Now, in the next week, from the Monday class onwards, I will start the actual flat syllabus. So, but for now, this session, we'll be concentrating on the automata theory basics. Yeah, so we're done with the formal language basics. Now we'll deal with the automata theory. The one actually designed by the Alan Turing. Okay. So going by the definition, what is an automata? Okay, or automaton, whatever it is. So an automata is essentially an abstract computational model. Okay, it's an abstract computational model that mainly deals with inputs, outputs, and states. If at all you need to write the definition of automata, this is the definition of automata. It is an abstract computational model that mainly deals with inputs, outputs, and states. So I will give you an example, right? All the basic models, input, some amount of processing, gives output. So this is pretty much an automata. Okay. So automata is a computational model which deals with inputs, outputs, as well as the states. We'll touch upon some applications of automata. Why we are studying this automata. Okay. So the first one is we have discussed in the previous session. Its application in formal languages, right? Many of the applications in formal languages, it can be dealt with the help of automata. Okay, how exactly it's going to happen, we'll see in the upcoming classes. Okay, but the main application of automata theory is in the formal languages. The next, very important one. This automata plays a main role in the designing of a compiler. So compiler designing. So in the next time, you will be studying this concept, compiler design in 3.2 as a continuation to the formal language and automata theory. Okay, so there, in order to develop a compiler for any new programming language, we need the automata theory basics, because this is the basic model, a basic mathematical model on which all the computers are based on. So the compiler is also not an exception. Okay, so in the designing of compiler also, automata is very, very important. Next, it plays a key role in switching theory in the electronics. In the previous session, I have explained this on-off switch, right? It's a basic switch. Initially, it is in the off state. If an electricity is given, it reaches on state. If the same electricity is removed, it again comes back to off state. So this very basic methodology is also used in the switching theory, which is in the electronics. Next, automata theory plays a key role in proving correctness of any problem. Okay, so let's say I have an algorithm or a program or a simple machine, a virtual machine, not the hardware machine. Its task is to take an input and check whether it is prime or not. Okay. You might be familiar with such kind of programs in your C and C++ laboratory, I think. developing, like checking whether the given input is a palindrome or not, prime number or not, composite or not. So all such kinds. So the pretty logic behind such proving authenticity programs is the automata theory itself, because we design the machine or algorithm in such a way that it accepts only certain kind of inputs. If the input fall in the category, then it is fine. If it is not, it is a failure. So for proving correctness of any system, any software system, in the same semester, you are having the subject software engineering, right? So in the software engineering, you will be dealing with many kinds of testing: unit testing, black box testing, white box, regression, agile testing, many kinds of testing. So behind all the testing methodologies also, automata theory is the base. Okay. Next, the design of algorithms. Okay. And lastly, the most advanced NLP and ANN, natural language processing and artificial neural networks. Many of the research scholars in South, let it be Karnataka, Maharashtra, Kerala, in the IITs and NITs, if you see many of the research scholars that's who are doing PhDs, they are dealing with this NLP stuff. They are training the machines in order to recognize the complex words in their own native language, like Kannada words, Marathi words, and all. So for all such research work also, the automata theory is the base. Okay, the same goes with the application of artificial neural networks as well. Okay, so that's why this automata theory is very, very important. It not only is a subject in one of the semester, but it serves as a core root methodology for many of the other subjects as well. So that's why it's very, very important to have a strong foundation in automata theory. Okay. So I have given the definition. Automata theory is an abstract computational model that deals with input states and outputs. If I want to like depict an automata, how I would? So generally, an automata is represented in 5 tuple format. Any automata will have 5 parameters, 5 tuples. So what are they? So it is Q, sigma, delta, Q naught, and F. All of you listen very, very carefully, even up to this point, if you are not attentive in the class, doesn't bother, but kindly do listen from this point onwards, because the whole of our first module of flat is based on this session. Okay, this is the base for the first module as well as the subsequent parts. If you are not solid in this foundation, then you can't understand the subject. Okay, so please be attentive with this part. Okay, so an automata is represented in 5 tuples. So these are the 5 tuples or 5 parameters. Q stands for states. So the states in the automata. Sigma is the alphabet, the input. Delta stands for transition function. Don't worry, I'll explain one by one very detailed. So delta is the transition function. Q naught is the initial state. F is the final state. Okay. So any automata can be represented with these 5 tuples. You need to understand, you need to know, and you need to remember the 5 tuples. Okay. Q, sigma, delta, Q naught, and F. This is the order. Okay. Q stands for states of that automata. Epsilon stands for alphabet or inputs of that automata. Delta stands for transition function. There is a formula, I will give it later. Q naught, initial state, F is the final state. Now, so all of this time we have been talking about automata. So how exactly an automata is and how exactly the questions will come. So let it be the midterm examination or the sem examination, the questions will be as follows. So design a finite automata or design a basic automata machine that accepts strings containing 0 and 1. For example, this is the base question. So design an automata that accepts the strings over the alphabet 0 and 1. This is how the question will go. Now, how to design a machine like this? So, as I told you, it should be following these 5 categories. So, see here, any automata, while you are designing any automata, first start with an arrow brace. Okay. Then Q naught. Because in the automata notation, Q stands for states. So, the small Q naught, we started as an initial state. So, this is the initial state always for any automata. Okay. So, Q naught, I will take an input 0. Okay. So, initially you are in Q naught. There is a state Q naught. If you take the input 0, you will come back to the same Q naught itself. Nothing will happen. But if you take input 1 from Q naught, if you take input 1, you will reach to some new state Q1. Okay. Again from Q1, if you take input 1, you will come to the same state. If you take input 0 from Q0, you will reach Q2. I will making it as a final state. Okay. Again from Q2, there is an option with 1, an input with 1. Okay. So this is a basic automata that accepts the strings over the alphabet 0 and 1. So this is how you need to construct the automata machines. An arrow brace, starting state circle with circles Q0 always. Okay, you can have inputs. This is not mandatory. I have just taken it. I have even removed it also. No issue. So the question is about 0 and 1. So that's why I have taken only 0 and 1. If the question is asked about A and B, I would have replaced it with A and B. Okay. So this is an automata that accepts the strings with 0 and 1. Okay. Q2 is the final state. So in order to make the examiner or anyone understand that like it is the final state, you should be representing it with 2 concentric circles. Okay. The initial state with arrow brace, the first arrow brace, initial state. For all the other states, apart from the final state, there is only 1 circle. But only for the final state, it should have 2 circles, just to have the differentiation. So now this automata will accept the strings over the alphabet 0 and 1. I will show you the strings. See, let's say first time in Q0, your process starts at Q0. From Q0, you can take the input 0. That means 0 has come. If you take 0, you will come back to the same place. If I take 1, I will reach here. I'm just traversing it over Seema. I have taken 0. I have come here. So 0 is encountered. I have taken 1. I have reached here. So 1 is there. Again, if I take 1, okay, I will reach again to Q1. If I take 0, I will reach here, Q2. Again from Q2, if I take 1, I will reach Q2. That's it. This is the final state. My journey is completed. So this automata is deriving this string 0, 1, 1, 0, 1. Agreed, all of you?
Sir, what is the logical reasoning behind this? Like how Q1
don't worry,
after
don't
giving
worry.
0
I will explain. Don't dwell too deep. Just view the concept. I will explain you all the cases and all. Don't worry.
Okay, sir.
All of you agreed with this one? This automata is deriving this string 0, 1, 1, 0, 1.
So
Now,
Sir, at the final thing, if you take any input, it will stay there only.
yeah, Q2 is the final state. That's why the 2 circles, it won't exit from this final state.
So whatever 0 or 1, it will be there only. It will not.
Yeah, it will be there here itself.
Okay.
Yeah, any other doubts, ma?
sir, what if we take 0 instead of 1 at Q2?
The last position will come as 0. That's it. I will explain all the cases. Don't worry. Okay. So now see, there is one more alternate also. I will start with Q0. I skip this 0. I will take 1 directly. So I will get 1. I will reach up to Q1. If I take 1 from Q0, I will reach 1. I have skipped this 0 in the second instance. Again, I have skipped this 1. From Q1, I have directly taken 0. I have skipped this one. Again at Q2, I have skipped this one. That's it. 1, 0 is my string. So in the same way, I can take 0. I cannot skip 1 because this is the only path in order to reach to the final state. So I will take 1, but I will skip this one. I have a feasibility. I don't take this one. Instead, I go directly to 0. Okay. I will skip this one also. I will be in the final state, 0. See, now this is a generalized machine. It is accepting randomly the strings with 0 and 1. But what if I have kept a restriction? The DFA or the finite automata should accept the strings ending with 0 only. Now what you will do? Ending with 0 only. Is there any modification you can do to this machine that so that the strings will be ends with 0?
You can replace the last one with 0.
Or even I can remove this also. All of you got it? Previously, the examiner or myself haven't kept any restriction. I want a automata machine that accepts the strings randomly 0 and 1. So for this, the previous machine with 1 is valid. Now, I want a finite automata that accepts the same 0 and 1, the input 0 and 1, but all the strings should end with 0 only. This is my restriction.
For every iteration, you'll have both 0 and 1.
No. Whatever be the prefix, I want the I want the strings that ends with 0 only.
So sir, 0, 1, 1, 0 can also be an option.
Yeah, that's it, ma. I have just removed the last input on the Q2 state. Previously, there is 1, right? So now there is not the such thing. Yeah.
We can put AND gate, sir. If we have 0 and 1 every time, if we put AND gate, we'll get 0 every time.
Nothing like gates here, ma. We only talked about the automata machines. So now is this valid? I will take 0, 1. I will take 1. With the help of this 0, I will reach the final state. From final state, I have nothing to do. This is ending with 0. Or if I simply skip the intermittent inputs, if I take 1 and 0, ending with 0. Or I can also take 0, 1. I will skip this 1. I will directly take the 0. Now all my strings are ending with 0, right?
Yes, sir.
Yes, sir.
All of you got the logic?
Can you explain once again?
Previously, there is no restriction. I want an automata that accepts strings 0 and 1. So that's why for every state, I have taken intermittent inputs. So even for the final state also, there used to be like this, 1. So if this is the case, there is a possibility that the final place of the strings will get 1, right? But now I want an automata that ends with 0 only. I want an automata that produces the strings that ends with 0 only. Now, if this restriction is placed, what I can do is I can simply remove the input on the last state. You are free to alter any of the inputs. Okay, there's no restriction. So now this machine, this automata will use the strings that ends with 0 only, right? So 0, 1, 1, 0. I will reach the final state. Nothing I can do. Or if I don't want the intermittent inputs, there's no mandate that I should take this. From Q0, I will directly take 1. I'll reach Q1. I skip this 1. I directly take 0. I reach Q2. So 1, 0. Or I will take 0. I take this 1. I reach Q1. I skip this. I skip the second input. I take 0 and reach Q2. So now whatever the combination you take, all the strings will end with 0. Now this machine is valid, right? For my concept. Okay. In the same way, if he asked, I want the strings starting with 0, or if I want the string starting with 0 and 1 mandatorily, you can design the machine such a way. For example, Q0, 0, Q1, 1, Q2, This string, sorry, this machine will only accept one string, which is 0 and 1. Because the process cannot halt in the midway. If you start here, you take input 0, you reach Q1. You take input 1, you reach Q2, 0 and 1. Okay. You're free to design your own machine, man. Okay.
Okay.
Guys, got it?
Sir, what is the
But-
difference between like if I make a machine of 1 0 and if I make another of 0 1 0? So will there be any difference like in the performance of that?
I didn't get your question, ma.
Like we are designing different machines, right, by our own choice.
Yeah.
But is like since we are designing different machines, like what difference will be there? How, like, will there be any difference how they perform like that?
There will be a clear-cut difference, ma, but that's not that we are dealing about. That's all comes under the part of design and analysis of algorithms, the efficiency, the time complexity, and all. Here, our task is to design the automatas. That's it. We don't worry about the efficiency, ma. How many steps it's going to take, what is the time complexity. That's not matters in this subject, at least. Okay, your task is to, given a question, you need to design an automata that is valid, ma. Don't worry about the efficiency.
Okay.
Sir, for the
Okay,
second example,
Hmm.
at Q0 initial state, can we take another intermediate input? Like if we take 1, it will still be a valid, sir, because 0, 1, 1.
Here,
No. Here, sir. Second example. You said it should be starting with 0, 1, no, sir. So can we take another intermediate input?
yeah, you can take 1 here. So that will give me 0, 1, 1. Or you can take 0, 1, 0.
No, not there, sir. At Q1.
Yeah, Q1.
And Q0 also. Q0.
Some intermediate inputs you are saying. Then
Yes,
there
sir.
is a possibility of the strings cannot be starting with 0, right? I want strings that starts with 0 and 1. If I take 1 here, there is a possibility for me to visit this path. So 1, 0 will come. So in that case, my string is not starting with 1.
Okay, then if we don't take
So based
Q0,
on the
then
restriction,
Q1.
you should be varying the machine. If I am saying that it should start with 0 and 1 mandatorily, then there's no intermittent inputs should be allowed. 0 and 1, then whatever be the iterations, you can do it in the final state.
We can still take at Q1, no, sir. We can still take intermediate input 1 as 1 at Q1, no, sir. It will be Q 0, 1.
Like this, you're asking?
No, sir. 0, 1, 1.
0, 1. 1. That's also valid.
Yes, sir.
That's what I'm saying. There's nothing wrong or right or like efficient or inefficient in automata. I want a valid machine. My notion is valid. What's your name, ma?
Varun, sir.
Varun, yeah, your notion is also valid. You can also take Q0, 0, Q1, you can take a 1, and then 1, you can reach final state. So that's also giving me 0, 1, 1 starting with 0, 1. I can have a 0 here. So 0, 1, 1, 0. There's no restriction in designing of automatas. Okay, you're free to go your own path. Okay. Actually, the discussion has been sidelined entirely, ma. Okay, yeah. So an automata can be represented in 3 ways. An automata can be represented in 3 ways. First one is transition diagram. Okay, the one we have seen just now. Okay, so in transition diagram, there are states depicted with circles. There will be directed arrows for the inputs, and the final state is depicted with the help of 2 concentric circles. Okay, this is the most approved like representation of an automata. Okay, there is also another way which is called as transition table. Okay, so if the examiner asks you to design an automata with the help of a transition table, then you should be taking a small table. So for the same input 0, 1, 1, 0, 1, right? The previous figure. So this is transition diagram, the first methodology. In the second methodology, if the transition table is asked, whatever be the input symbol, you make it as columns. See here carefully, 0 and 1 is the input. So I have make it as a columns. And what are the states? You make it as rows. So Q0, Q1 and Q2. Okay. Same for the initial state, keep it with arrow. For final state, you can write like this, or you can simply keep a star mark, an asterisk. That's it. So now Q0 on 0. What is that you are reaching?
Q0.
1, 1.
No, Q0. Ma. See, Varun, Q0. If you take input 0, what is that you are reaching?
Yes, got it,
State.
sir. Yes.
Yeah, Q0. So from Q0, if you take 1,
Q1.
Q1. So if from Q1, 0.
Q2.
So from Q1, if you take the input 0, you reach Q2. Q1 on 1. From Q1, if you take the input 1, the same Q1. So Q2 on 0.
So this will be same only Q2.
No, Q2 on 0, there is no input from 0, right? From Q2, there is no 0, there is only 1.
Nothing, sir.
Yeah, so leave it. Okay. This is the second methodology. This is how you can write an automata. Then there is one more methodology, which is transition function. Now, previously in our session beginning, I have told you to keep it aside, right? There is a formula I will explain you later regarding the transition function. So the third tuple delta, the transition function, it is of the form Q cross sigma is Q. So essentially, from a state, Q is a state, right? If I take any input, sigma is input, right? So from a state, if I take an input, what is a state? Again, I'm reaching. That is my question. Okay, for example, delta, I will take state Q0 and I will take the input 0. What is that I'm reaching?
Q0.
Q0. So this is how you need to write the transition functions for the same DFA. So delta Q0 of 1.
Q1. It's Q1.
All of you understand?
Yes, sir.
Yes, sir.
All of you getting the concept? So this is the third methodology of writing an automata, transition function. So you should write like this, delta, function of delta. You have to take these two parameters inside the function, a state and an input. The result should be a state. So Q cross sigma is Q. This is how the mapping should be. So from Q0, if I take the input 0, I will reach Q0. So this is how you should write. So delta of Q0 comma 1. So from Q0, from state Q0, if you take the input 1, what is the state you are reaching? Q1. Okay. So the same continues. Okay. So these are the three ways of writing an automata. Okay. If the examiner asks you to choose one particular notation, write that one. If it is not specified, by default, go with the transition diagram. Because first thing, it will appear beautifully in the writing view. Second thing, error rectification is very easy. So previously we have seen, if I want an automata that ends with 0, if you simply removes this, by mere observation, you can say, yes, this is valid. The same in case of transition table or function, it's very, very complex. Okay. I hope you can visualize the things. No need to write an example and explain you. Okay. So if the examiner asks you to write whether in table or function, there's no other alternate. If he asks in table, write the table. If he specifies as a function, write as the delta format. If at all not specified, by default, you go for the transition diagram because it occupies more space. Okay. As it is a simple example, there is only 3 states. Coming in the further classes with the previous, I mean, complex concepts, there will be 17 to 18 states as well. So first thing is it occupies much space. Second thing is it appears beautifully. Obviously, a picture is greater than 1000 watts, right? So it appeals very much to the examiners, and error rectification is very easy. You can simply observe the automata and say whether you have designed the problem correctly or not. Okay. So always go with the transition diagram.
Sir, there Q1 intermediate can we write as 0, sir?
Where ma?
In transition diagram. Then upward arrow. Can we write 0 there? If we write 0, what will happen, sir? Like that. Can we write, sir?
No. There is some restrictions. I should not go like that. I will explain in the next class. Okay, there are the types of automata which goes like 2 different fashions. From one state, if you take one input, it will reach one state. In order to reach the same state, there are 2 different inputs. There are types of automata. This is just a basic. Okay. Don't worry, from the next class onwards, we will touch upon all the cases and all the concepts. Don't worry, I will give you as many examples as possible to practice. Okay, I hope everyone are clear with the automata basics now. B1, are you clear?
Yes, sir.
What are the 5 tuples?
States, alphabet,
just tell me
transition
the
function,
names
initial
itself.
state, and final state.
Q, sigma, delta, Q naught and F. So you should be familiarized with this terminology. Q, sigma, delta, Q naught and F. What is Q?
State.
So all the states. So for this, tell me Q. What is Q?
Q0, Q1, Q2.
So Q0, Q1 and Q2. Now all of you clear? So for this automata, the Q states is Q0, Q1 and Q2. What is the alphabet?
0, 1.
0 and 1. So in this automata, the inputs are 0 and 1. So my alphabet of input is 0 and 1. So sigma is 0 and 1. What is delta? We have seen, right? So all these delta components. Q0 of 0 is Q0, Q0 of 1 is Q1. So the same you can write in the delta, the transition function. What is the initial state, ma?
Q0.
Q0. What is the final state?
Q2.
Q2. That's it. Okay. So an automata is represented in 5 tuples. The states, input, function, initial state and final state. There are 3 ways. First one is diagram, the most efficient and better version. So the initial state should start with arrow symbol. The final state should start with, should depicted with concentric circles. Transition table, columns, you take inputs, and rows, you take states. Okay. So this is the one. So here also, always remember, the initial state should be represented with arrow brace. And in the table, you can have 2 circles or asterisk for the final state, just to distinguish it from the other state. That's it. And transition function, this is how you should be writing. So delta of state comma input is state. This is how the function should be mapped. So these are the 3 methodologies. Okay. So in the Monday session, we will be starting with the types of automata and all such examples. Okay. Yeah, thank you all. That's it for today, ma. Have a happy weekend.